Yes, Mariam. What's the direction of area vector? Mariam, direction of area vector. Amalia, what's the direction of area vector?
Z-axis.
Perpendicular to area. Huh?
That's
Direction
right.
of area vector is perpendicular to area. So theta is the angle between area vector perpendicular to area and magnetic field. So angle between area vector and magnetic field is known as theta. So we have phi, which is B dot A, which could be written as BA cos theta also. So this is how we calculate magnetic flux, which is BA cos theta. After magnetic flux, the next is it's a scalar quantity. Magnetic field is vector, area vector is vector, but after dot product we get a scalar. So it's a scalar quantity. Its SI unit is, see, its SI unit is the SI unit of magnetic field multiplied by the SI unit of area. Shahzada, what is the SI unit of magnetic field?
So Newton per meter.
It's magnetic field.
Tesla
Newton per
meter.
meter. Tesla.
Yeah, sir. Tesla.
Tesla meter.
It's Tesla. And what is area meter square? It's Tesla meter square.
Yes, sir. Clear.
Or this you can write as Weber. So it's Tesla. This T stands for Tesla. Tesla meter square is equal to Weber. That's the SI unit. Its CGS unit is Gauss centimeter square, which we call as Maxwell. CGS unit is Maxwell. This unit is very important. If you look at previous year's questions from first book of class 12th, this particular unit is being asked many times. What is the CGS unit of magnetic flux? Maxwell. 1 Weber is 10 raised to the power 8 Maxwell. Note it down. Then we will do few questions on this concept. Tell me once you have written or scroll it down.
Yes, sir.
Okay. Any doubt, Abdullah?
No, sir.
So school is still online or it's offline now?
It's online.
Online, sir.
Online. Next,
Can you scroll up?
yes. Next exam is in November only, na?
Yes, sir.
Yes, sir. I guess so.
So before this, some part is there, right?
Which one?
Right before this. Up.
Sorry, I didn't get you.
So can you move up? I didn't write that part.
Okay.
This area vector.
This one?
Yes, sir.
Sure. Tell me once you have written. No, Noor, Weber is the SI unit. Maxwell is the CGS unit. Tesla meter square is Weber. CGS is Maxwell. Huh? Gauss centimeter square.
Okay, sir.
So what is that scalar?
Scalar. This magnetic flux is a scalar quantity.
Okay.
Next. The next is see next question. Magnetic field of, let's say, 2 Tesla exist in XY plane. Calculate flux through an area of 5 meters square if field lines are inclined at 60 degree to the plane of area. So you have a magnetic field of 2 Tesla. This exists in XY plane. Calculate flux through an area of 5 meters square. Field lines are inclined at 60 degree to the plane of area. So the question is, this is your area. This is the direction of area vector. Direction of area vector. This is plane of area. This is plane of area. This is magnetic field. So what is 60 degree? It's the angle between magnetic field and plane of area. This angle is 60 degree. See, this 60 degree is not your theta. The theta that we use here in flux BA cos theta, this theta is the angle between magnetic field and perpendicular to the area. So what is this angle in this case?
30 degree.
30 degree. They are perpendicular. You can write that theta is 90 minus 60 is equal to 30 degree. So in calculating flux, when I write the expression of flux as BA cos theta, don't get confused with this theta. This theta is not the angle between magnetic field and plane of area. This theta is the angle between magnetic field and perpendicular to the area. If angle with the plane is given, then subtract it from 90 degree to get angle with the normal. Now you can substitute all values. How much is magnetic field? It's 2 Tesla. How much is area? It's 5 meters square. then it's cos 30. So you will get magnetic flux is 10. Cos 30 is root 3 by 2. So it's 5 root 3 Weber. Is it clear?
Yes, sir.
Okay, just note it down. Then we'll do one more question on the same concept.
So why did we use Web
Which one?
and WB? Why did we use
WB
Lect?
is the unit.
We can use Tesla meter square, right?
You can use Tesla meter square. You can write it as Weber. That's your choice.
Yes, sir. Clear.
Note it down. Then we'll do one more numerical on the same concept. Tell me once you have written.
Yes, sir. Done.
Okay.
Done, sir.
See the next question. The next question says magnetic field B equal to I cap plus 2j cap minus 3k cap Tesla exists in space. See, from this given data, you should be able to decide that magnetic field is given in Cartesian form. I cap, j cap, and k cap component is given. When you have a vector in Cartesian form, then usually you don't need angle. You just need another vector also in Cartesian form. So from this much data, you should be able to decide that magnetic field is in Cartesian form, then area vector should also be in Cartesian form. If it is not given in Cartesian form, then we'll try to convert it in Cartesian form. Cartesian form means in terms of I cap, j cap, and k cap. Don't find angle between the vectors. In Cartesian form, we don't try to find the angle between the vectors. So magnetic field B is I cap plus 2j cap minus 3k cap Tesla exists in space. Calculate flux through an area of 3 meters square in, let's say, XY plane. This area of 3 meters square is placed in XY plane. I need flux through this area of 3 meters square. So, Nazira, your area is in XY plane. So what should be the direction of area, Nazira? If an area is in XY plane, then what is Z axis, right?
Sorry, Z axis.
Area is always perpendicular to the plane. So if your plane is XY, then area will be along direction of area along Z axis. So area vector is, it's 3 k cap meter square. So we have both magnetic field as well as area vector in. This is not given, it's a part of solution. It's given that area is in XY plane. That means its direction is along Z axis. Along Z axis, we can use a unit vector k cap. If you want to write this in terms of I cap and j cap, you can write this as 0 I cap, no component along x axis, plus 0 j cap, plus 3 k cap meter square. Next is I need magnetic flux. Magnetic flux is the dot product of magnetic field and area vector. So it's I cap plus 2j cap minus 3k cap dot, it's 0 I cap 0 j cap plus 3 k cap. Now, if you take dot product, the coefficient of I cap is 1 here and the coefficient of I cap is 0 here. So you can write this as 1 into 0. When we take dot product in Cartesian form, then what we do is we multiply ith component with the ith component. We multiply jth component with the jth component. Then we multiply kth component with the kth component. So multiply 1 with 0, 2 with 0. The component coefficient of j cap is 2 here. Coefficient of j cap is 0 here. K cap is minus 3 and k cap is 3. Plus it's minus 3 into 3. So this is 0 plus 0 minus 9. So this is equal to minus 9. So this is magnetic flux 5B, minus 9. Is it clear, Mariam?
Yes, sir.
So whenever we take dot product in Cartesian form, we multiply ith component with the ith one, jth component with the jth one, and kth with the kth component. Note it down. We'll do one more numerical on the same concept.
Done, sir.
Okay. Next question. Solve this question also. Magnetic field is given, it's I cap plus 2j cap minus 4k cap Tesla. And area vector is given as I cap minus j cap plus 5k cap meter square. Get the value of flux. Get the value of magnetic flux. Solve it and write your answer in chat room. Okay, Abdullah. Abdullah is correct. Good. Any other answer? Good, Noor. Mariam, Fatma. Yes, Noor. Correct. Nazira, just check your calculations, bache. You're making some minor mistakes in calculation. Ahmad, Shahzada,
Sir,
Fatma, Mariam.
Sir, I answered.
You answered on. Say, I'm the faculty. Yeah. I am the faculty, the co-host.
so is that okay now?
Sir, I sent the answer.
Okay, Fatma is correct. Ahmad is correct. Nazira, just check your calculations. Mariam, Amalia, Shahzada. Answers.
Sir, you didn't get.
Amalia, no, Amalia, you're doing wrong. Just check the previous question.
Sir is the co-host Mariam.
Mariam, I didn't get your answer till now. I got the answer Fatima. Mariam, basically, what's your answer? Just you can. Yes, Mariam, it's correct now. I'm good. Got your answer. Amalia, you're doing it wrong. Shehzada.
Yes, sir.
It's a 1 mark. Yeah, it's a 1 line question. See, just take the dot product. Nah? No, Amalia. Amalia, see. Yes, Shehzada, you're right. 4k cap dot. Amalia, when we take dot product, then we don't write I cap, J cap, K cap. See, coefficient of I cap is 1 here, I cap is 1 here. So multiply 1 with 1. No I cap. I cap is 2, J cap is 2 here, J cap is -1 here. So multiply 2 with -1. Coefficient of K cap is -4 here, 5 here. So it's -4 multiplied by 5. So when we write it, this is 1 minus 2 minus 20. It's minus of 21 Weber. Amalia, is it clear now?
Yes, sir.
Sure. So that's magnetic field. I cap plus 2j cap minus 4k cap, I cap minus j cap plus 5k cap. So that was about magnetic flux. After magnetic flux, we will do Faraday's law of electromagnetic induction. Faraday's experiment first. So first of all, listen something. So what are the different sources of voltage or EMF that you know? Can you name me some sources of EMF, some sources of current? Battery or cell. That's one source of EMF or current. Any other source?
Motor.
Motor, no. Motor doesn't generate EMF. Motor use EMF to rotate.
Wind turbine.
Which one? Moving turbine.
Wind turbine.
Turbine basically connect with generator, right?
Yes, sir. So
You want to say
generator.
generator.
Yeah.
Any other source you can think of? So till now I got two sources. One is a cell or battery and another is generator. Any other source of current or EMF? See, the power that's coming to your home, it's generated in some type of AC generator only, yeah? So when we talk about the sources of current or EMF, we have two types of sources. One is cell, another is generator. Whatever the power that you're getting at your home is generated by some generator, or we call it dynamo. In the power plant, there is a dynamo which is generating that EMF or current. It doesn't matter what type of plant is it. If it is an hydroelectric power plant, or it's a thermal power plant, or it's a nuclear power plant, or it's a solar power. Solar is something different, or it's nuclear power plant. In all these plants, it's a generator which is generating the EMF. Third type of source is solar cells, or we can say that's again a type of cell basically. So we have two things, one cell, another is generator. Before this Faraday's law, before this guy Faraday, there was only one source of EMF, and that was cell. Whenever you have you need voltage, you need current, you take a cell, connect it to the circuit, you can get current. There was no other source than cell or battery before Faraday's law or before Faraday's experiment. Faraday did a very basic experiment, and from his experiment, he concluded that we can generate EMF by just changing flux. I'm repeating it again. At the time of Faraday, there was only one source of EMF, and that was current. Through his experiment, Faraday proved that one can generate EMF just by changing flux, magnetic flux. If you can change magnetic flux related with a system, you can generate EMF. That is known as Faraday's experiment. After Faraday's experiment, after Faraday's law, then come Tesla. He used this Faraday's law and he made a generator or a dynamo. First dynamo was built by Tesla, but that dynamo, that generator is based on Faraday's law. This was this guy Faraday who shows that change in flux can generate EMF of change in flux can generate magnetic field. So in Faraday's experiment, what Faraday did, and try to imagine like this experiment, Faraday was doing this experiment at a time where people believe that only one source of EMF or current is possible, that's current. People like Edison was there at that time. They believe there can't be any other source than the cell or the battery. So what Faraday did is he take a coil, he connect this coil to a galvanometer. This is a galvanometer. See, there is no cell, nothing, just a galvanometer. What do you think? There should be any current in the circuit or not?
No.
There is no cell, no battery, no source of EMF, nothing. There should be no current in the circuit. What should be the deflection of the galvanometer? It should be 0.
0.
Then what Faraday did, he take a magnet, north pole and south pole of the magnet. This magnet will generate some magnetic field. So this magnet is generating a magnetic field. This magnet generates some magnetic field. The magnet is generating some magnetic field. So what is the flux? You can see if magnetic field is passing through this coil, that means some flux is linked with the coil. If the magnet is stationary, then flux linked with the coil is constant. So I can write if magnet is stationary, then flux linked with the coil is constant. So if magnet is stationary, then the flux linked with the coil is constant. So you can write this as flux is BA cos theta, which is equal to constant. Magnetic field is constant, area of the coil is constant, angle is constant. I'm not rotating magnet or this coil, so it's a constant flux. If flux is constant, that means no induced EMF. No induced EMF means there is no EMF. Deflection in the coil would be 0. But when you start moving this magnet towards the coil, Fatma, can you decide if this magnet moves towards the coil, then out of these 3 parameters, which one will change? B, A and theta, if magnet is moving towards the coil. So can you guess which parameter will change? Magnetic field change, or the area of the coil will change, or the angle will change?
Magnetic field.
Magnetic field will change. Very good. Shazada, can you decide when we take magnet towards the coil, then magnetic field will increase or it will decrease? If you're bringing a magnet close to yourself, then the strength of magnetic field, what happen with the strength?
It will increase because it will attract more.
Yeah, it will increase, right? So when yes, Abdullah.
That theta will also change, right? Or
No,
will
theta is not changing. I'm not rotating the magnet. I'm just bringing it in the same direction. So magnetic field will remain in this direction only. Area of the coil remain as it is only. Only the strength is changing.
Okay.
Angle will change when I rotate the magnet or I rotate the coil. When magnet moves towards the coil, then B increases. Okay, when B increases, Nazira, what happened with the flux? If B increases, then what happened with the flux? Flux will remain constant, it will increase or it will decrease. Yes, Nazira.
It will increase.
It will increase. Hence, flux increases. Huh? When I say flux, means magnetic flux. And as the flux increases, EMF induced in the coil. EMF induced in coil. But this increase it, this induced EMF will last till the flux is changing. Once the flux becomes constant, like you take this magnet and make it stationary, the EMF will be zero again. You will have EMF only if the flux is changing. You move this magnet and then you make it stationary near the coil. Flux is constant, EMF will be zero. EMF will induce only if the flux is changing. Is it clear, this experiment?
Yes, sir. Yes, sir.
Now, Faraday repeat this experiment several times in different forms. What he did, once he take this magnet towards the coil, flux is changing, EMF is inducing. Then he take the magnet away from the coil. If he's taking magnet away from the coil, Shahzada, what will happen with the magnetic field now?
So it will its strength will decrease.
Its strength will decrease. And how will it affect the flux?
Like
If B is decreasing, how will the flux will change?
it will increase.
Flux depends upon magnetic field. No? It's directly proportional
So
to
it
B.
will,
It will also decrease. So if flux decrease, then again you will have EMF. But once you bring this magnet stationary, flux will be constant. See, if you bring this magnet stationary, flux is not zero, flux is constant, but EMF would be zero. You will get induced EMF only if flux is changing. Then you bring the coil towards the magnet, then you bring the coil away from the magnet. In all cases, whenever you change flux, you will get induced EMF. Once your flux is constant, the induced EMF would be zero. He did several experiments. I'll send you a sheet containing all the experiments by Faraday. But in all experiments, this thing is common. Flux is constant, EMF zero. If flux change, then EMF will change. I'm showing you a small animation. For this concept. Okay. So this is the coil, this is the galvanometer. Magnet is stationary, so there is no deflection in the galvanometer. Now see, this magnet is moving towards the coil and see the pointer of the galvanometer, it's deflecting. He make this magnet stationary, the deflection is zero. Then he's again taking this magnet away from the coil. When it's taking this magnet away from the coil, see the deflection of the galvanometer. It's again deflecting, but in opposite direction now. That means the direction of current has changed. So that's one experiment of Faraday. He did several experiments like then after the magnet, he brings this is interesting. So when he is bringing the magnet towards the coil, it's the magnetic field lines. Magnetic field lines, some flux is linked with the coil. When this magnet enters inside the coil, then the flux changes, flux increases. Due to increase in flux, you get a deflection. And when he bring this magnet away from the coil, then the flux decreases. Due to decrease in flux, flux is again changing, deflection would be in opposite direction. Now, it's not necessary that he should always bring the magnet. Instead of magnet, he can bring a coil also. He bring one coil which is carrying current. So this coil will generate some magnetic field, right?
Yes, sir.
This coil will generate some magnetic field. So this coil will generate some magnetic field. So this current carrying coil will behave like a magnet. See, this is the key. This key is closed. This is the key here. This key is closed. When the key is closed, some current is flowing through the coil. Ahmed, that negative and positive are just relative. The important thing is the direction is changing. That's it. This that negative and positive is not according to this problem. We'll discuss how we decide the direction of the current or the EMF. But the important thing is when it's moving the magnet towards the coil, then the deflection is in different direction. When the magnet is moving away from the coil, the deflection is in opposite direction. So what he did is he bring a coil. This coil is carrying some current I. This is the key. But if you can see, there is no deflection here. There's no deflection because it's generating some magnetic field. But see, we are not moving the magnet or the coil. Huh? This behaves like a magnet. We are not moving this coil. We're not moving this magnet. So the flux is constant. But see, that's why the deflection is 0. But see now, what he did is he just switch on the key. See, as such a switch on the key, you can see the deflection. There is a deflection here. See, as soon as he switched on the key, there is a deflection in the galvanometer. The current is flowing. There is no deflection, but he switched on the key. There is some deflection. See, what's the cause of this deflection? What happens is as soon as he switched on the key, the current in this coil starts decreasing because it's no more connected to the battery or cell. The current starts decreasing. When the current in the coil starts decreasing, the magnetic field which this coil is generating will decrease. When the magnetic field decrease, the flux linked with the second coil decrease, and that decrease you can see in the form of deflection. There is deflection in the galvanometer. There is this deflection in the galvanometer. When he again switched off the key, there is again a deflection, it again becomes 0. So when you switched, like open the key, means you decrease the current, then there is a deflection because flux is changing. When you close the key, at the instant you close the key, the current increases from 0 to a maximum value. Current is increasing in this particular coil. Here, flux will change here, and you can see a deflection in the galvanometer. So in all cases, if flux is changing, you will get an induced EMF or induced current now. Okay, now questions. Ahmed, can we also generate flux by changing the current, increasing or decreasing the current? Yes, Ahmed, current can always generate flux. Na? In chapter number 4, we did when current passed through a coil, it generates some magnetic field. If you have magnetic field, that means you have flux. Now we are doing the reverse thing. Like if you have magnetic field, you can generate current. If you have EMF, that means you have current. Okay, now doubts. Abdullah, any doubt in Faraday's law?
No, sir, all clear.
Fatma,
No doubt, sir.
Nazira.
Sir, it's clear.
Okay. So whenever you have change in flux, you will have EMF. If your flux is constant, that means your induced EMF would be 0. Okay. Let's stop it. So on the basis of these experiments, Faraday proposed a law which is known as Faraday's law of electromagnetic induction. Okay, before starting Faraday's law, write this experiment. This is one experiment. Faraday did 4 experiments. I will share this thing. I will share a PDF having all experiments. Note it down. Just 1 second. Just give me 1 second. Give me 1 second. Just 1 second.
Sir?
Yes. Just 1 second, Abdullah.
Okay.
Just 1 second. Yes, note it down. Yes, Abdullah, you're asking something?
No, sir.
Can I scroll it?
Yes, sir.
See, the next is Faraday's law of electromagnetic induction. So Faraday's law basically says if you change magnetic flux, then you will have some induced EMF, and it tells you how to calculate that induced EMF. So Faraday's law says whenever magnetic flux linked with a coil change, an EMF is induced in it. And if the circuit is closed, then a current is also induced. If circuit is closed, then a current is also induced. First thing. So whenever flux change and EMF induce it. The second statement of electromagnetic induction says, how would you calculate that EMF? We know that if flux change, then EMF induce, but how would you calculate that induced EMF? So the second statement says that induced EMF is equal to rate of change of flux. So this statement will give the mathematical formula for the calculation of flux. Like at some time t1, the flux is phi1. At another time t2, the flux is phi2. So flux is changing. So at time instant t1, flux is phi1. At time instant t2, flux is phi2. In time interval delta t, delta t is t2 minus t1. In this time interval, the change in flux is delta phi is phi2 minus phi. So we can say that induced EMF E is proportional to rate of change of flux. Rate of change of flux means change in flux with respect to time. It's proportional to delta phi by delta t. So this is equal to K times delta phi over delta t now. When you remove the sign of proportionality, the value I'm writing directly the value of K, that's minus 1. So it's minus of delta phi by delta t. This is induced EMF. This negative sign basically represents a law which is known as Lenz's law. We'll discuss Lenz's law. Lenz's law will tell the direction of current and the direction or polarity of EMF. This Lenz's law will give you the direction of induced current. What is the direction of induced current? What is the polarity of induced EMF? That is given by this Lenz's law. So negative sign here represents Lenz's law. So I should write that negative sign represents Lenz's law. Represent Lenz's law. So is minus of delta phi over delta t. So negative sign is representing Lenz's law. This EMF is an average EMF. But if you want to calculate instantaneous EMF, for instantaneous EMF, you can write this as E is equal to minus of limit delta t tends to 0, delta phi over delta t. E is minus of limit delta t tends to 0, delta phi over delta t. When you take this limit, you can write this as minus of d phi over. So for average EMF, we will divide change in flux by time. But for instantaneous EMF, you will simply differentiate flux with respect to time. And again, here also, this is Lenz's law. Negative sign represents Lenz's law. Now, if R is the resistance, then you can also calculate induced current. So the current induced in the circuit is the ratio of EMF and resistance. That you can write as minus 1 by R d phi over dt. So this is how we calculate induced current. It's minus 1 by R d phi over dt. Does anyone of you remember the relation between current and charge? Through this relation, can you calculate charge? Change in charge flowing through the circuit.
Is 2 by d.
Which one?
I is equal to Q by T. R is Q by T.
So you can write your I as dq over dt, which is minus 1 by r d phi over dt. So see, this dt will cancel this dt. You can write that the charge will be, it's minus 1 by r into d phi. Change in charge. So this is it. This is Faraday's law. Faraday's law of electromagnetic induction. Note it down. We'll do some questions over it.
Sir,
Yes.
if circuit is closed, then the current is also
Induced.
okay.
We don't have current in open circuit. We have current only if the circuit is closed. Noted?
Yes.
Okay, now write this question. So you have a magnetic flux. Phi is equal to 3t square plus 2t minus 1 Weber is linked with a coil. Calculate EMF induced coil in first part. T equal to 0 to t equal to 2 seconds. Second part. T equal to 2 seconds. So here interval is given. Where interval is given, that means you're supposed to calculate the average EMF. Here instant is given. When the instant is given, you're supposed to calculate the instantaneous EMF. Note down the question first. Note down the question first. Huh? Noted?
Yes, sir. Done.
Shahzada?
Yes, sir.
Okay. Solve it. Solve and write your answer in chat. Okay, Noor. Okay, Abdullah. What about the rest? Mariam, Amalia? Okay, Ahmed. Nazira? Okay. Okay, Abdullah. It's okay. Okay, Malia. Nazira, do you know how to differentiate? Nazira, you know how to differentiate a function?
Yes, sir.
Okay. Then do it. Mariam, are you doing it?
Yes, sir.
Shazada,
Yes, sir.
I got answer from Abdullah, Noor, Ahmed, and
So I
Amalia.
just randomly said.
Ahmed, I got your answer. Shazada, Nazira, Mariam. I'm waiting for answers. Okay, Mariam, what about the second part? Okay, I'm solving it now. Okay, see. First part. So induced EMF is minus of delta phi over delta t now. So delta phi means it's minus of phi 2 minus phi 1 over it's t2 minus t1. It's phi 2 minus phi 1 over t2 minus t. So how much is t1? T1 is 0 seconds. How much is t2? T2 is 2 seconds. How much is phi 1? Phi 1 is, just put the value of t in each equation. 3 into 0 square plus 2 into 0 minus 1. So phi 1 is minus 1 Web. When we need phi 2 is 3 into 2 square plus 2 into 2 minus 1. So phi 2 is 12 plus 4, 16 minus 1, 15 Weber. So you can write that EMF, just substitute all values here. It's minus of phi 2, which is 15, minus of minus 1, divided by T2, which is 2, minus 0, minus of 16 by 2. So your induced EMF is minus of 8 volt. That's minus of 8 volt. This is induced EMF. Second part. At t equal to 2 seconds means you have to calculate the instantaneous EMF. For instantaneous EMF, you can write this as it's minus of d over dt of phi. So it's minus of d over dt of phi is 3t square plus 2t minus 1. It's 2t minus 1. So EMF is minus of, when you differentiate it, you get 6t plus 2 minus 0. So you get EMF is minus of 6t plus 2 now. This is the equation of EMF. You need EMF at t equal to 2 seconds. Huh? So when you put t equal to 2 here, EMF is minus of 6 into 2 plus 2. So EMF is minus of 14 volt. Yes, Nazira, is it clear?
Yes, sir.
Sure. Okay. It's noted down. We'll do few more questions on the same concept. Can I scroll it further?
Yes, sir.
Okay, the next question on the concept is, the next question will use a solenoid as well as the toroid. Okay, solve this question. A square loop of side 10 centimeter and resistance of 0.7 ohm is placed vertically in the east-west plane. A uniform magnetic field of 0.1 Tesla is set up across northeast direction. The magnetic field decreased to 0 in 0.7 seconds at a steady rate. Calculate induced EMF. Do it. and write your answer in chat. See, theta is given as 45 degree. Northeast means 45 degree. Answers. See, it's very easy. Theta is given, magnetic field is given, square is given, so you have area. Using BA cos theta, get the value of flux, initial flux, final flux is 0, and the time taken to change the flux is 0.7 seconds. So you can calculate phi 2 minus phi 1. Phi 2 is 0. Phi 1 you can calculate using BA cos theta. And this T2 minus T1, that time is given as 0.7 seconds. Do it.
Sir,
Yes.
sir, the initial time is 0, right?
The initial time is 0. Yes. That 0.7 seconds is the time interval. Delta T, T2 minus T1 is given.
Sir, this resistance has any use in this question?
Yeah, for current. Resistance you will use to calculate current. Huh?
Yes, sir, but now we just need EMF, right? So no use.
Yeah, basically in question we're also asking to calculate current.
No.
I didn't mention current, but EMF and current. Okay. While measuring EMF, resistance is of no use, but when you are calculating current, then you will need resistance. See, if you understand Faraday's law, then the entire chapter is very easy. It revolves around the Faraday's law. So the very small chapter, just 3 to 4 topics in this chapter. Answers? Okay, Amalia. Very good. Noor, you're doing some mistake. You're making some mistake. Amalia, just check your unit only. Yeah. Some powers. You're issuing some powers. Okay, Abdullah. Okay, Ahmed. See. First, let's calculate flux. Initial flux is B A cos theta. That's the initial flux. So a square loop of side 10 centimeter and resistance 0.7 ohm is placed vertically in the east-west plane. A uniform magnetic field is set up across northeast direction. So northeast means see, if this is your coil, this is the plane of your coil. Huh? East-west, this
Yes,
is your
sir, this is
coil is placed. This is coil. This is north-south direction. Huh? Northeast direction, sorry. This is north and this is east. This is the direction of magnetic field. Northeast means it's bisecting. This angle is 45 degree and this angle is 45 degree. So theta is 45 degree. Your magnetic field is given. How much is magnetic field? It's 0.1 Tesla. Magnetic field is 0.1 Tesla. Area will be side square. One side of the square is given. So area will be 0.1 square. 0.1 square is 0.01 meter square. When you do all these substitutions, you will get that your initial flux is B, which is 0.1, into area, which is 0.01, into cos 45 degree. So you will get that your initial flux is 10 raised to the power minus 3. Cos 45 is 1 by root 2 Tesla. That's 5. Now, what about the final flux? The final flux reduced to 0. Magnetic field reduced to 0. That means flux reduced to 0. Phi 2 is 0 now. How much time it takes to reduce to 0 is 0.7 seconds. So delta T is 0.7 seconds. You can easily calculate induced EMF. It's minus of delta phi over delta T. It's minus of phi 2 minus phi 1 over T2 minus T1. So induced EMF is minus of phi 2, which is 0, phi 1, which is 10 raised to the power minus 3 by root 2, T2 minus T1, which is 0.7 seconds. So the induced EMF is 10 raised to the power minus 3, and this is 0.7, and it's root 2. Root 2 is 1.414, or it's 1.414. So 0.7 into 1.414 is almost equal to 1 if I use calculator, because 1 by 0.7 is equal to root 2. So 0.7 multiplied by 1.414 is 0.99. So 10 raised power minus 3 divided by 0.99. So it's almost equal to 10 raised to the power minus 3 volt only. That's the EMF. So if you know EMF, you can calculate current. See, current is EMF by resistance. So it's 10 raised to the power minus 3 divided by resistance. How much is resistance? It's 0.7. Shazada, is it clear?
Yes, sir.
Nazira, any doubt?
No, sir. It's clear.
Okay, note it down. Then we'll do one more numerical. One more numerical on the same concept. Tell me once you have read. Change the slide.
Done, sir.
चलिए next देखिए. नेक्स्ट ये सीबीएसई का पुराना क्वेश्चन है. देखो. So you have a coil with an average diameter of 0.02 meter is placed perpendicular to magnetic field of 6,000 Tesla. If induced EMF (11 volt) when magnetic field is changed to 1,000 Tesla in 4 seconds, what is the number of turns in the coil? What is the number of turns in the coil? So induced EMF is, you can write, if you have n number of turns in the coil, it's minus n phi2 minus phi1 by T2 minus T1. So see, magnetic field is given, initial is given, final is given, EMF is given, radius is given. Try to get the value of n, number of turns in the coil. Note it down.
What will be theta for phi?
Yes.
So we need to calculate phi, right?
Which one?
We need to calculate phi.
You have to calculate n number of turns.
No, so for that we need to calculate phi 1 and phi 2, right?
Yeah, you need phi 1 and phi 2. But if the diameter is given, that means you can calculate the area of the coil, right? It's pi r square.
Yes, sir, but I'm thinking about the angle.
You have diameter, do it now. Okay, I'm solving it now. So this is minus of n. Phi 2 is area multiplied by the magnetic field. Area multiplied by the initial magnetic field. Then this is T2 minus T1. Now what you can do is you can take this area outside. So EMF is minus an area because flux is area into magnetic field. It's B2 minus B1 over T2 minus T. Next, you need the value of N. So substitute all values. How much is E? E is, see, all terms are given. E is 11 volt. How much is B1? B1 is 6,000 Tesla. How much is B2? B2 is 1,000 Tesla. T2 minus T1 is the time interval. How much is the time interval? That's 0.7 seconds. Sorry, that's 4 seconds. So if you substitute, and what is area? Area is pi r square. How much is radius? How much is radius of the coil? Radius of the coil is half of diameter. Then how much is diameter is 0.02. (0.01 meter). So if I make all these substitutions here, I will get A is equal to pi 0.01 square. So your area is pi 10 raised to the power minus 2 square. So your area is 10 raised to the power minus 4 pi meter square. So you have all parameters, you can get the value of n to it. Abdullah, n is 28, not 26. And that's the answer. N will comes out to be 28. When you do all these substitution, n will comes out to be 28. Note it down. So this completes Faraday's law. In the next class, we will do Lenz's law.
Sir, can we neglect minus sign?
Yes, because yes, you can neglect negative sign because number of turns can't be negative. Note the angle is 0 degree. Yeah? Plane of area and magnetic field is 90 degree, but perpendicular to the area and magnetic field is 0 degree. Yeah? That's why cos 0 is 1.
Now angle is 0 degree.
Angle between area and magnetic field, because when we calculate flux, we write this as phi is BA cos theta. Theta is 0 degree. Ahmed, clear? Yes, Abdullah, class is over.
Okay, sir.
Thank you, sir.
Love is. So make all these substitutions here and get the value of n. The value of n will comes out to be 28. So Lenz's law, this Faraday's law is over. Let's stop here. We'll continue this in the next class. Okay. Allah Hafiz.
So